So what's the determinant of 1 minus MP? The first repeat of this guy. You know, R is very easy to put in. Well, that's just the product of eigenvalues, which I'll write in the following way. I'll write them as expanding eigenvalues. So 1 minus lambda P expanding. And 1 minus lambda P contracting, expand, contracting. And the number of expanding plus number of contracting plus 1, because there's one marginal direction along that we have eliminated. That's the whole dimensionality of the space. So maybe I should call this D. So, you know, unstable manifold, stable manifold. Now we want to have an absolute value of this guy, so we put absolute value around this. These guys are smaller than 1 in magnitude, doesn't matter, they're complex. So I can only put absolute value here. And now it's natural to pull out this product, LP E over expanding, and write times the product expanding of 1 minus 1 over LPE. Now this is smaller than 1, so the absolute value just comes here. And early in the course I defined this to be instability of an orbit, the product of all unstable eigenvalues. That was the important stuff. And now it's being modified by corrections which are exponentially small for long orbits. Because for long orbits, multiplier grows exponentially with the period, and this. So these are corrections. So, you know, I just divided multipliers of the matrix or eigenvalues of matrix into the ones that are larger than 1 in magnitude, smaller than 1. Then I've decided to pull out this larger than 1 factor collected, and the correction is smaller than 1 term. And now we do a physics thing, which we say, let's just drop this, guys. So that's what you do for rev letters. And then what happens, and now I'll use a different letter. You get a formula that says that this is E to the minus sum over periodic orbits. LP to the power R, because all the eigenvalues get raised to the power if I put R's here. So these are the repeat number. Over, you know, C and C to the NP times R, E to this thing times R. So everybody is raised to power R. So now I can use my definition of expansion of logarithm. So let me call TP, let me call it Z to the NP, E to the, you know, all that stuff, AP minus, but not repeated, just once, minus S to the P divided by RP. So this now just becomes, you know, plus sum over P. I can sum this R, that's the definition of logarithm, so it's logarithm of 1 minus TP. And, you know, if I have something here that's a product, an exponent of logarithm is it, it's 1 minus TP. So the zeta function that I introduced originally for counting, topological zeta function, is actually an approximation to the determinant. And It's an approximation which should be good, and you can prove it for the leading eigenvalue. You know, you're interested in the leading eigenvalue here. This leading eigenvalue of your operator, which says that longer cycles have some very small exponential corrections. I can drop them. So now this formula is extremely easy to use. It's not the best one, but it's pedagogically the easiest one to learn how to use the stuff. When you actually compute and you have control over, if you have found 3 periodic orbits and you don't know, you've gone fishing, you came back with few orbits, you don't know what they are, what are you missing, etc., then all this stuff is useless because, you know, you have no control. But if you got into a situation where you know all the short ones and you know how to make sure that you pick up the next longer ones, then this starts working. So, you know, you really need to understand topology of the problem before this starts working. But you get this amazing formula. It says I only have to compute all prime cycles, only, you know, infinitely many of them. But then we already saw that we can arrange it as a power series and truncate and have shadowing, etc. So that's what I'll exploit next time.